Next lesson following the previous lesson is non-contact forces. This is still part of the categories of forces, right? Where we're looking at the types of forces that we have. So another type of force that we have really is non-contact forces. So non-contact forces are really an opposite of contact forces. These are forces that exist between objects that do not touch each other. So these objects are able to interact with each other, exert forces on each other, but without touching each other. This is a very simple force to study at this stage. It can get to be really interesting when you look at it from the perspective of Newton's universal law of gravitation. But for Newton's laws, when you want to do the calculations of Newton's laws, it becomes very quick and simple. And there's only one non-contact force, the gravitational force, what we call the gravitational force. Now, to understand the gravitational force, imagine yourself on the Earth's surface. You are standing on the Earth's surface, and then you place a box. You place a box on the air, right? You want to put the box on the air. You want to put it there for it to sit there. But what happens to the box? The box suddenly goes down. It moves and it goes down, right? So when you try to put the box on the air, it drops, it goes down. Why is that the case? What's pulling it, right? There must be some form of a pull. Remember how we define the force. You must remember where we started lesson 1 if you want to get this. Please go to lesson 1, revisit lesson 1. We said a force is a pull or a push. So we see that when we try to put the box on the air, something pulls it, right? So experiments and research has been done, right? And they came to learn that actually the box is pulled by the earth itself, right? By the earth itself, right? But without touching it. Hence we say this force is a non-contact force, right? So how we define this force is that we say it's an attraction force that the earth exerts on any object directly towards its center. So what we learn about this force when we conduct our experiments and we do our research is that this force is always directed towards the center of the earth. Remember that the earth would be something like that, right? And the center would be here. So the force is always going towards the center, right? It's directed towards the center, right? And it happens without the earth touching the object, really. That's why we say it's a non-contact force. Now, the formula that defines this force is given by Fg. So the symbol for this force is Fg is equals to mg, right? Now, let's try to explain this. The m here stands for the mass of the object on the Earth's surface, right? So it's measured in kilograms. Now, I will define mass in the next lesson properly, especially when I do Newton's first law properly for you. But for now, let's understand mass as, something that measures how big, it's a physical quantity that measures how big or small an object is, right? And we measure it in kilograms, right? So obviously, if an object is big and an object is small, it will experience a different gravitational force, as we have defined here, the gravitational force. The G there stands for the acceleration due to gravity, and this is a constant. As long as we are within certain heights, we are at lower heights, we're not at greater heights, right? It always becomes a constant of 9.8 meters per second squared. And this, you also get it on your formula sheet. They give you on your formula sheet as part of the constants there. If you forgot this one, you can always go to the formula sheet to check it, right? Then the G, of course, stands for the gravitational force that the earth exerts on the object, and it is measured in kilogram meter per second squared. Now let's talk a bit about this. If you look at this formula and you substitute. Okay, let me write this formula in full so that we don't get confused. So here we have Fg is equals to mg, the mass times the acceleration. We know that the mass is measured in kilogram, and we know that the acceleration is measured in kilogram meters per second squared. So this means I'll have a unit for force, right? Because this is Fg is the force, is m meter squared. So we'll have kilogram meters per second squared, right? But remember, we already had said when we started our lessons in lesson 1 that force is measured in newtons, right? So this would mean that when you see a kilogram meters per second squared, it is the same, it is equivalent to 1 newton, right? That's another way of writing it. So what I'm saying is that if you have something like, you know, 5 kilogram meters per second squared, it will be the same as 5 newton. If you have 10 kilogram meters per second squared, it will be the same as 10 newton, because they're exactly the same in proportion, right? This 1 is to 1, if we can put it that way. And there isn't much really to study here, except we'll talk more on this and expand on this on a different lesson, mechanics part 3, where we study the universal law. I've put that aside because I think it deserves attention. I didn't want to put it here and to be part of this, right? So just to go again, as it, you have seen now maybe that it's a culture that after we have gone through our concepts, we really go into doing a question, right? Remember that always when we approach a question, we have our academic constitution that says, I can solve this problem, right? It's a mindset that we have when we approach problems. Now, here we start by interpretation, which involves reading the question, writing down the direction, and choosing the direction and writing down the given information as well, right? So here question 1, they say an object of mass 10.2 kg rests, right, meaning it does not move, on top of the table, right? And we can see here on this diagram that this object is rested there, right? So one thing that will come to mind is that this table doesn't fall down. Why? Because we discussed, in our previous lesson, when we were discussing the category of forces that are contact forces, that the surface of the table is pushing this box with a force that is directed vertically upwards. So that the box doesn't go down, and we call that force the normal force. It makes an angle of 90 degrees here with the surface of the table, right? But also we just learned now from this lesson that also the earth, because it's on the earth's surface here, this is the earth here. The earth also is exerting a force, a non-contact force, without touching the box, right? On the box, I'm going to focus on the box here because, there's also forces on the table, but I'm going to focus on the box because they gave me information, or rather the mass of the box and all that. So I'm going to focus on the box. So the earth is also pulling the box vertically downwards with a force Fg, we just discussed now, right? So what I've done now here is that I've interpreted our problem, right? Reading, I think maybe also one thing that I can do also is that maybe I can come this side and say this is question 1, right? And I'll choose direction. Now in this case, I'll use the reference frame. I will say, look, anything that goes to the left is positive, anything that goes up is positive, right? And then I'll write my data just to finish off my interpretation, right? I'll say here I have the mass is 10.20 kg. I know this is the mass because I can see it's measured in 10 kg. In fact, I was even told on the problem. Another thing that I haven't been told, and this is also actually part of problem classification, is that I'm going to write the acceleration due to gravity to say it's 9.8 meters per second squared, because I can see that this box will experience the acceleration due to gravity, and I can already see that when we solve this problem, the theory that can come in mind is the idea or the knowledge that we have just read now of the force of gravity, the gravitational force, right? Another thing that comes to mind is that maybe they may ask me to draw a free body diagram to find the net force, because I have two forces acting on one object here. So we can use that equation that we started with in lesson 1 of the net force. Maybe they can ask that. I'm trying to do what here? To classify what they can ask me. And I think at this stage they can even ask me any theory that we have done. They might say, define what the free body diagram is, define what the force diagram is. Those are the things that I expect to be asked when I look at this question here, right? So let's go through the question itself to see if our classification is going as expected. So here they say, draw a free body diagram of the forces acting on the object, right? Remember that this here, we call it a force diagram. We call this a force diagram, right? And already from a force diagram, we can take out a free body diagram, can't we? We can take out a free body diagram, right? And again, this question of a free body diagram, they like it a lot, because that's how they test if you know the definition of a free body diagram, you know what a free body diagram means. So this here would be the normal force that goes vertically upwards. It makes a 90-degree angle with the surface. And here we'll have the force of gravity as well, right? That is Fg, right? And that's how you answer that. Again, you have to pay attention to your mark allocation. So this is to say here that this will be 1 mark. My pen is failing me. Why? So this will be 1 mark, and this will also be 1 mark. You get that 2 marks there. Now, if we go to question 2.2, they say calculate the gravitational force, right? So this, again, as part of our classification, you can see that we use the formula as we just discussed it now. This would be 10.20 times 9.8. I mean, this would be roughly 10.2 times 9. Okay, 10.2. I'm trying to do it with my head, so let me just focus on the calculator because I'll waste time now. So this would be 99.96 Newton, right? 99.96 Newton, right? And of course, this answer, when you look at it, so already what we have done as part of our academic constitutions, that we're here on answer, right? Hence we're answering the question and doing the calculations. Now I want to navigate the problem. I want to see if this answer makes sense, right? Now if you look at this answer here, I'm multiplying 10.0 by 9.8, right? This is like more like saying 10 by 9. You expect it to go closer to 100, right? So it makes sense for a mass of 10 point that is not too big, it's not too small. It's an answer that really makes sense, right? And if sometimes you want to change parameters here, I can say, okay, if I were to put half of this mass here, how will this change? I expect to get that to be half, right? So if I were to say 10.2 divided by 2, I make it half, it's 5.1. So if I say 5.1 times 9.8, I expect to get half of this, right? 49 point that. If you say 99.96 divided by 2, that gives you 49.8. So I know that my answer is, it does make sense. It's around the expectations of what makes sense, right? Grade 11s and grade 12s, thanks for staying tuned for this lesson. This was a quick one. as I'm saying, we're trying to build a foundation here to solve more complex problems, but you need to have these small pieces so that you can be able to deal with a bigger picture. Please always don't forget to like and subscribe. Leave your comments in the comment section, and also feel free to send us an email at it's here at the bottom, scienceless@outlook.com, with questions that you have, or maybe topics that you want me to create videos and break down the concepts for you before you write exams. Share those questions that you're trying to do but they give you difficulties, so that I can assist you before you write your exams. See you in the next lesson. May the force be with you.